Hello, I'm Patty Simpson with Simpson Math. In this video, we're going to introduce the normal distribution. So before we get to that introduction, let's first talk about the difference between continuous data and discrete data. In the past, when we've looked at probability distribution, we've been dealing with discrete data. A fixed number of times that we roll a die or we spin a spinner. Everything that we've done up till now has been discrete data. So our random variable was something that was countable. Our x values were 1 or 2 or 3. They were nice and countable numbers. We are going to be looking at variables now and collecting data that is continuous data. In other words, we'll be looking at things like the height of a person. With height, our height we can measure more and more accurately, so we can get that continuous type of data. Fluid ounces, the length of a butterfly's wingspan, that type of thing, where we're looking at continuous variables. So when we talk about the normal curve, we're talking about continuous data. Then I want to remind you that probability and area are related. So remember when we did spin the spinner and I asked you, what's the probability that the spinner lands here? You told me that it was 1/4. That probability was 1/4 because that area of the circle made up 1/4 of the circle. Or when we drew our symmetric sample space, we could see the area of that sample space is what gave us our probability. So probability and area are related. That's a big deal when we're talking about our normal curve. Then I want to jump to college algebra for a second instead of statistics. And let's just look at this function where we have 1 over x squared plus 1. And I'm going to graph that function for you. This function this rational function looks something like this. So let me just graph this function, and I'm just going to make an x and y table to plug in some x values and get out some y's. And let's just look at what this particular function looks like. So this function, when I graph it, let's put in, let's start with say a 0. Let's just start at 0. If I put 0 in for x, I get 1 over 0 squared plus 1 gives me 1 over 1, which equals 1. So when I put in 0 for x, I get out 1 for y. So I know on this particular graph, there's a point at 0, 1. We'll make our 1 pretty big here. Then, if I put in a number like 1 for x, 1 over 1 squared plus 1, well, 1 squared is 1 plus 1 gives me 2, so my output there is 1/2. So when I put in 1 for x, I get out 1/2 for y. So here I have 1 for x, and I get out 1/2 for y. Let's put in 2 for x, so that I have 1 over 2 squared plus 1. Well, that's 4. 4 plus 1 gives me 5, so I end up with 1/5. When I put in 2, I get out 1/5. So when I put in 2, I get out 1/5. About there. I want you to notice that as I put in larger and larger numbers, say we put in something like 10 for x. If we put in a really large number like 10, well, 10 squared is 100. 100 plus 1 gives me 101. I would end up with a little fraction, 1 over 101. So it gets littler and littler, teenier and teenier as we go further and further out. But say I pick 1,000 or 1,000,000, I'm still just going to end up with a really big number on the bottom. So my fraction just gets smaller and smaller, but I never make it to 0. We call that asymptotic behavior, so that this is decreasing and getting closer and closer to 0, but never reaching it. That's called asymptotic behavior, so that there's an asymptote where y equals 0. It's getting closer and closer to that, but never reaching it. Let's look and see what's happening on the other side of our graph. If I were to put in negative numbers, say I put in a -1. Well, if I put in a -1 for my x, -1 squared is still equal to 1. Plus that 1 still gives me 1/2. So on the other side, I also get out a half when I put in that -1. What about if I put in -2? Well, if I put in a -2, again, -2 squared is 4. 4 plus 1 gives me 5. So I still end up with 1/5. So this function is symmetric. And in fact, if I put in a -10, I'm going to get out, well, a -10 squared is going to be 100. 100 plus 1 is still 101. So it's still getting closer and closer to 0 without ever reaching it. So here we have that same asymptotic behavior on the other side. We've graphed that function. Now, this function is similar to the normal curve that we're going to be looking at. The normal curve has a lot of the same attributes that this particular function has. By that I mean, the normal curve is going to be symmetric, just as this function is. The normal curve also has this asymptotic behavior, just as this function does. So these two functions, the normal curve and this function, are very similar in their looks and characteristics there. So when we draw our normal curve will have this same shape and same idea of being symmetric and having that asymptotic behavior. So you've done a little college algebra for the day. Feel proud of yourself. Let's now talk a little bit about calculus. So in calculus, when we do this integral, what we are doing is we are finding the area underneath that curve. So see that this curve here, when we find the integral in calculus, we're talking about the area of it. You know, we're used to finding the area maybe of a rectangle where we just do length times width. Well, finding the area of a curve is a little more complicated than that. But in calculus, we can do that. We can find the area underneath an entire curve. And that's called the integral. So we find this whole area that keeps going that way because that graph keeps going that way forever. And this whole area underneath the curve. And we find out, if you do some calculus, we find out that this particular area is equal to pi. So if you were to find the area underneath that curve, it would be pi. But in a probability density function, remember with our probability distributions that we had, all our probabilities had to add up to 1. So in a probability density function, in a function that looks like this, like the normal curve, but we're talking about a probability density function, the area under that curve is equal to 1. So when we find the integral of it, the area under that curve is equal to 1. And so that's exactly what this says. It just says that the total area underneath the curve in a probability density function is equal to 1. So a normal curve is a PDF, a probability distribution function. And it's going to have these characteristics where it's symmetric and it has asymptotic behavior. And then it's really important to remember that because we know the area under the curve is equal to 1, we're going to be able to find some probabilities for parts of it by looking at how much of the area under the curve is being, the spinner's landing on, you could think of. And then we're going to be dealing with continuous data. In the next video, I'll actually show you the formula for the normal distribution, and we'll talk a little bit more about it. Math Made Simple, it's Simpson Math. Thanks for watching.